This is Srikanth S, Assistant Professor of EEE Department. In this session, I am discussing the single loop generator and losses present in the DC generator and how the power stages will be there in DC generator we are going to see. So here single loop generator is nothing but how a voltage is generated in a single coil. In a single coil, how the voltage is building and how we are converting that particular AC component into DC, we are going to see clearly with the pictorial representation. And here we are taking the two conductors, conductor A and conductor B, and the conductor A which is connected to the slip rings A and slip ring B. So these two will form one coil, and when it is at exactly 0 degrees, when it is at exactly 0 degrees to the magnetic field, 0 degrees to the magnetic field, according to Faraday's law, it has to induce the voltage, and that voltage is proportional to rate of change of flux linkages. Here the flux linkage, when it is at a 0 degrees position, the flux linkage is 0, which is very less value. We are considering it as 0. So the value will be 0 here. When we change the position of the coil, when we change the position of the coil by 30 degrees in anti-clockwise, 30 degrees in anti-clockwise, then if you see here, when it rotates, here the A also starts rotated and B also rotated. Slip rings have rotated along with this. So when this is rotates, the flux cutting is increases, because here completely flux is cutting by the conductors. So when the flux cutting increases, automatically E is proportional to d phi by dt. When d phi by dt increases, voltage will increase. When d phi by dt increases, voltage will increase. Here the voltage is increased. And if it still rotates by 30 degrees, if it still rotates by 30 degrees, that is at 60 degrees position, the voltage will still increases. And here also A is rotated, B is rotated, A is connected to Q, B is connected to P. So like this, when the position of the rotor, when the position of the coil changes, the voltage will increase. And if you take exactly at 90 degrees position, so the maximum flux is cut by the conductors. So we are going to get the maximum voltage. We are going to get the maximum voltage. So then after, when we take at 120 degrees condition, when we take at 120 degrees condition, again here the voltage is decreases. This is just like exactly at 60 degrees. This is the value at which we got at 60 degrees. And then after, when it rotates by 150 degrees, again this is the value which is same as the value at 30 degrees. And when it rotates by 180 degrees, the position completely shifted, but at 180 degrees we are getting the 0 voltage, because the flux cutting is 0. Now if you see, this is the B position, this is the A position. Here it is reversed. When the position of A and B are reversed, it has to generate the negative voltage when it rotates. But because of these slip rings which are connected, we are going to get the positive voltage. Let us see the next. When it rotates, here the slip rings, whatever the B phase is connected to Q and P phase is connected to Q. Q is connected to B and P is connected to A. And here the positive voltage which is coming, here the negative voltage which is generating. So the negative voltage is, which is because of these slip rings, these are connected. These are connected to Q and P. So because of these slip rings, we are going to get the positive voltage itself. Because of these slip rings, we are going to get the positive voltage when it is connected, when it is rotated by 30 degrees, that is at 210 degrees. Again, the voltage which we are going to get is similar to the 30 degrees and 150 degrees position. And like this, if you go on rotating the conductor by 360 degrees, like this, we are going to get the voltage buildup in the conductors, so that we are going to get the complete DC voltage by having the slip rings. And these slip rings will form when number of slip rings are connected together. These slip rings are going to form a commutator. That is commutator. What is the function of commutator? Which converts AC supply which is generated in the DC machine is converted into a DC. Now let us go with the EMF equation of DC generators. Here we have seen how the EMF is generated, that is because of the rate of change of flux linkages. And the EMF which is generated is in the conductors, and because of the rotation speed and some constructional details. Now let us consider phi is the flux per pole in Webers, which is the main field flux, and Z is the number of conductors in the armature, and N is the speed of armature, that is in revolutions per minute, and P is number of poles, and A is number of parallel paths in armature. And we have seen the number of parallel paths for wave winding, it is 2, for lap winding, which is equals to number of poles. And E is the EMF induced in any parallel path or generated EMF. Here, according to Faraday's law of electromagnetic induction, the average EMF which is generated per conductor is equals to d phi by dt, that is rate of change of flux linkages. Here flux cut by time taken, and flux cut per conductor in one revolution. Flux cut per conductors in one revolution is equals to d phi is equals to phi into how many number of poles are available, that is phi into p Webers, and number of revolutions per minute is n by 60, n by 60, and time taken to complete one revolution is 60 by n. Time taken to complete one revolution is 60 by n seconds. Now, if we substitute these values into the EMF generated per conductor equation, now d phi by dt is equals to phi p by 60 by n, that is equals to phi pn by 60 volts. Phi pn by 60 volts. This is the EMF which is generated per conductor. Remember this. Now we are going to have Z number of conductors. We are going to have Z number of conductors, and we need to calculate the EMF generated across complete winding. So we are going to have in the winding, we are going to have some number of parallel paths. So EMF generated is equals to average EMF generated per conductor into number of conductors in each parallel path. Number of conductors in each parallel path, that is equals to 5 Pn by 60 into Z by A volts, where A is equals to P for lap winding and A is equals to 2 for wave winding. So which is equals to EMF is equals to 5 Pn by 60 into Z by A. This is the voltage equation or EMF equation in DC generators. Now let us go with one problem. A 4-pole generator having wave wound armature winding has 51 slots, each slot containing 20 conductors. What will be the voltage generated in the machine when driven at 1500 rpm, assuming the flux per pole to be 7 milliwebers? Flux per pole to be 7 milliwebers. Here we need to calculate the voltage generated in the machine with the given data. Here the wave wound armature which is given. Wave wound armature is nothing but number of parallel paths 2, which has 51 slots. Number of slots are 51, and each slot containing conductors, which is equals to 20 per slot. 20 conductors per slot. So the total number of conductors will be total number of conductors is equals to 51 into 20, that is equals to 1020 conductors. Now what will be the voltage generated in the machine when driven at 1500 rpm, assuming the flux per pole to be 7 milliwebers? Here the flux per pole is given as 7 milliwebers, and it is given A is equals to 2 because it is a wave wound. So A is equals to 2. So here N is equals to 1500 rpm, 7 into 10 power minus 3 flux into number of conductors 1020 into 1500 by 60 into number of poles are 4 divided by number of parallel paths are 2, which is equals to 178.5 volts. Now we will go with the losses which are going to occur in DC machine. Here, in any machine, we are going to have the losses, and this DC machine is a mechanical or rotational machine. So, which is going to have the mechanical losses and electrical losses. And these mechanical losses and electrical losses are the mechanical losses when it is rotating, that is rotational losses we are going to occur, that is frictional loss. Because of the bearings we are going to get some loss, that is of frictional loss, and then because of the air gap we are going to get some windage loss, and these two losses will be constant for particular machine. Even though you increase the load on the machine, the losses will be constant. These losses are constant because of these are corresponding to mechanical parts, that is depends on the constructional features of DC machine. So here this is now we'll go with the electrical losses. These electrical losses depends on the resistance of the conductors which we have used for place for creating the winding. Based on that, we are going to have one is armature copper loss and field copper loss, shunt field copper loss, and series field copper loss, which is going to have the field winding copper loss and armature copper loss. And copper loss is nothing but I square R loss. That is based on the current, how much amount of heat which is developed in the conductors. That depends on the I square R value. And the next one is the stray load losses. In this, we are going to have that is hysteresis losses and eddy current losses. These are nothing but based on the property of a core material which we have used. That is based on the BH curve, that is magnetic field and magnetic field intensity. Based on the BH curve is going to have some curve. When we increase the field intensity, the magnetic flux density will increase. When we decrease the magnetic field intensity, immediately that will not become zero. That will have some value because of magnetic property. That is, when let us take one example. If we play with a magnet with iron particles, the after certain time, the iron particles also will be having the property of magnetism. That is, they are going to attract the other parts of iron particles. So this is one of the examples. So it takes some time to lose the magnetism. So that will take some time. So this will create a loop between B and H. The area under this loop is called the hysteresis area. The hysteresis area, based on the hysteresis area, the hysteresis loss of that particular magnetic material depends, that is equals to neta B max power 1.6 F into V. This is the hysteresis loss. And the next one is the eddy current loss. Here, because of the leakage of the magnetic flux density or leakage of the eddy currents, we are going to get this loss. This loss is also simply, it is also a I square R loss. The loss in the magnetic core, copper loss in the magnetic core is called eddy current loss. That is equals to Ke Bm square F square V square T square. These are the empirical formulas. So here the eddy current loss depends on proportional to F square and N square. Here the losses are based on the value, how it is going to change. Based on that, the losses are classified into two different losses. One is constant loss, another is variable loss. The losses which remain constant at all loads are known as constant losses, and these losses are constant throughout a machine. That is iron losses, mechanical losses, and shunt field losses. These losses will not vary even though there is a load increased on the machine or load decreased on the machine, or any other parameter changes, also these losses will never change. These losses are constant. And whereas variable losses are nothing but the losses which vary with load are called the variable losses. That is copper loss in the armature winding, because when the load on the machine increases, the current value increases. When the current value increases, I square R value increases. So the copper losses will be the variable losses along with the armature winding, and in the field winding, the copper losses are variable losses. Now we'll go with the power stages in the diagram. Here, this power flow diagram is used to determine the efficiency of a generator or motor. In the below figure of power flow diagram of DC generator, it is shown that initially the mechanical power is given as input, which is converted into electrical power, and the output is obtained in the form of electrical power. That is, there are various losses such as friction, windage, stray losses, and core losses. Here you can see immediately after giving the mechanical input, immediately after giving the mechanical input, first we are going to get the mechanical loss. That is, we are going to lose some amount of energy in the form of heat. That is called mechanical loss. And then after we are going to get the iron losses. This loss is in the magnetic core. This stray load losses and iron losses are in the magnetic core. We are going to get these losses, and these after reducing from the mechanical power input minus this mechanical iron and stray load losses. These three are the constant losses. After deducting these three losses from the mechanical power input, we are going to get electrical power developed. Electrical power developed. And once the electrical power is developed, once the electrical power is developed, some current will start flowing in the armature. Because of that current, armature is going to experience some heat. That heat is in the form of, that heat is nothing but the armature copper loss. That heat is nothing but armature copper loss. And along with this, we are going to generate some voltage in the field winding also. So because of that, we are going to get the shunt copper losses. After deducting this shunt copper loss, we are going to get the electrical power output. And these are after developing the electrical power, whatever the losses were occurring, those losses are the variable losses. Those losses are nothing but variable losses. These are the constant losses, and these are the variable losses. So in this, we have discussed the power stages. Now let us discuss the efficiency of DC generator. Here efficiency is nothing but efficiency is equals to output power by input power. Output power by input power, that is equals to, what is the output power we are getting? Vt into IL. That is the output power. And in order to get the input power, what we have to do? We have to add all these losses, that is constant loss and variable losses are going to add, so that we are going to get the input power Vt into IL plus WC is the constant loss, WCU is the variable loss. This is the efficiency of the DC generator. How we are going to calculate. So here IL and WCU are going to vary with respect to the current flowing through the generator, whereas WC value is constant throughout the calculation of efficiency. And in this session, we have discussed the basic single loop generator and what is the EMF equation and what are the different power stages and different losses present in the DC generator. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.